Good morning, everyone, and thank you for joining our event. My name is Theodoros Papalas, and as the chair of the Early Career Chemical Engineer section of the EFCE, I'm very happy to welcome you to our fifth webinar of the Coffee Talk series. A little bit about our section. The Early Career Chemical Engineer section is planning to bring together all the early career chemical engineers across Europe and to give them different upskilling opportunities and also to network with each other. And one of the activities that we do is the current Coffee Talk series, where we are inviting the different working parties of the EFCE, and we give them the chance to introduce themselves to us and to talk a bit about the fundamentals of their working field and also the activities that they do. Today, I am very happy to have the Coffee Talk with the Chemical Reaction Engineering Working Party. And this event will be moderated by Dr. Luca Mastroianni, and who is a general member of our section, and also Mr. Alper Koyuncu, who is a board member of our section and also the leader of the Coffee Talk events. I would also like to mention that the event is being recorded and it will be uploaded later on the YouTube channel of the EFCE. And with that, I'm ready to pass the floor to Luca in order for him to kick off the event. Luca, the floor is yours.
Yes, hello everyone. It is for me a great pleasure to introduce these worldwide known speakers today. I would like to start by introducing Professor Van Geem. Kevin Van Geem is a full professor in the Faculty of Engineering and Architecture at Ghent University. He is the director of the Center of Sustainable Chemistry and also the director of the board of the Laboratory for Chemical Technology of Ghent University. Moreover, he is the CTO of Capture, which is an inter-university platform grouping 100 faculty members of different universities with the ambition to accelerate radical technological innovations in the field of sustainable resource recovery. His main research interest is reaction engineering in general, with a specific focus in the transition from fossil to alternative resources, such as biomass, CO and CO2, and plastic waste. He is a former Fulbright research scholar of MIT and a visiting professor in Stanford. He is in charge of the pilot plants for chemical recycling, oxidative coupled methane, steam cracking, biomass pyrolysis, and super dry reforming. He is also author of more than 300 scientific publications. He holds 3 patents and is the managing director of his own spin-off company on modeling of steam cracking. He is involved in electrification, process intensification, machine learning and data mining, drug design, scale-up, and process modeling. So welcome very much, Professor Van Geem. Moreover, I would like also to introduce Dr. Jan Verstraete, who is a senior researcher at EFP Energie Nouvelle. He holds a PhD in chemical engineering from Ghent University on fundamental kinetic models for catalytic reforming of naphtha. He joined IFPEN Lyon Research Center in 1994, working on the modeling of various refining processes. From 1999 onwards, he was appointed as a project manager for applied projects on heavy oil processing, successively working on fluid catalytic cracking, residue hydrotreating, ebullited bed hydrocracking, solvent deasphalting, crude oil upgrading, and crude oil chemicals. In this position, he coordinated IFPEN's processes, development research with industrial companies. His current activities include silane separation by means of simulated moving bed processes and plastic pyrolysis. The more fundamental aspects of his research concern multi-scale composition and reactor modeling. He is also co-author of 53 scientific publications and 2 book chapters, and he holds over 30 patents. So you can see that we are very good speakers today. I will briefly introduce the agenda of the meeting. We will have about 20 minutes presentation from the speakers, which will be followed by about 50-20 minutes Q&A section. It will start with with the questions prepared from us, from the early career section, and then there will be also a Q&A from the audience. So if you have any question, please write it in the chat box. I hope everything is clear, and therefore I would like to give now the voice to Professor Van Game to start his presentation. Thank you very much.
Thank you for your very nice introduction. So I will try to share my screen, and I hope you can see it.
Yes.
So I will briefly introduce the Working Party on Chemical Reaction Engineering. And that's, of course, the European division. So we have also branches in other continents. So I will start with the foundations of our Working Party. So as you can see, we have a very long history within the European Federation of Chemical Engineering. And it always has been one of the key scientific working parties in this organization. It's also one of the largest working parties with also numerous contributions then to the conferences organized by the European Federation. Our ambition is really to bridge the wall between science and industry. So we really want to connect what's happening on the molecular scale with the industrial scale. So that also translates in the members in our working party. Some people doing very fundamental research. A lot of other people do very applied development, also at companies. The sustainability, electrification, and digitalization are really also the, I think, most novel topics that we are working on. So I think this working party started originally from, I would say, the classical fossil-based industry, but then we have moved substantially. And we basically also are the bridge between the national societies. So we try to coordinate on a European level, and we try to share knowledge of the field of chemical engineering and specifically reaction engineering. So what is our mission? So we really want to advance chemical reaction science. This is both fundamental and applied research, and important word there is really kinetics, but also catalysis and reactors. So kinetics is really about reaction rates, and catalysis allows to speed those up, and the reactor is then the unit that basically is used to create a certain conversion. And this is all on the process level. So again, very fundamental theoretical work, but also real things in practice. So we also have members in our community which actually builds large-scale units which are implemented then in industry. Obviously, we want to develop our community and basically make sure that there's room for the excellent talent which is available in Europe, especially in the chemical engineering world. So, and we try to encourage collaboration and also support early career researchers to build a strong connected community. Societal challenges are, of course, key. So we have climate change, we have energy transition, and of course, if we look at now what's happening on the AI front, then this also creates new opportunities, but also challenges, also especially for our field. If we look at the technical scope of reaction engineering, then again, we focus on this kinetics, catalysis, and reactor design, but I think the applications have really moved over the past decades from, I would say, the classical fossil-based industry to biomass, to plastic waste, to basically e-fuels. So The fundamentals remain the same, but the applications have evolved. In that respect, the advanced reactor systems, and then I speak about typically process intensifications, which involves microreactors, but also very advanced reactors, then play a key role. Yeah. So process intensification is basically a complex word for doing more with less. So smaller reactors, less energy, and preferably also electrified technologies, but electrified technologies with green electricity. That's the only way to reduce our carbon footprint. Digitalization and sustainability also play a key role. So we had a very nice seminar lately on AI with 4 excellent contributions on many aspects of AI, machine learning applications, but also very integrated multi-agent AI systems for modeling complex petrochemical plants, but also biomass and CO2-based plants. If you look at our activities and the platforms that we have, so our, I would say, most important conferences are related to chemical reaction engineering, but you have ISCRE and ESCRE. And ISCRE is the international symposium. So we had that about a week and a half ago. In this case, it was in South Korea. And ISCRE starts from the 50s. And typically between 400 and 600 people are present there in this area. So in the meeting in Seoul, we had about 600 people being present. Next to ISCRE, we also have ESCRE, which is the European equivalent, and that conference will be organized next year in Milan. So there we have more or less a similar size of people meeting, but then really focusing on the European side. So we have about 400 people again meeting there at these events. And there, of course, we meet also as a working party to discuss the future of our working party, but also new topics. Yeah. So the networking is also quite important in these international meetings. So next to these conferences I already mentioned, we have, of course, the EFCE and the CISA conferences, where also the reaction engineering community is largely present. And we are very active in these spotlight webinars. And for the last, I think, 5 years, we have now organized those together with the process intensification working party, with a focus on electrification, AI, and application of process intensification and reaction engineering. So in this way, we foster cross-disciplinary advances in reaction engineering. Obviously, we also have what we call business meetings. And these business meetings happen once or twice per year, where all the working party members join and we discuss the agenda and also the future of our working party. Yeah. So clearly, we want to encourage young researchers to delve into our field. We had a large presence in Seoul, but the field of reaction engineering is really, really crucial for this energy transition and for reducing our CO2 footprint. So in that respect, we try to explain to people why reaction engineering actually matters and what the big picture actually is, and why we are actually doing all this sometimes very fundamental work. Yeah. We also discuss about the education curriculum, and we try to learn from each other how we can improve the curriculum and incorporate new aspects such as sustainability and electrification. Yeah. And in this way, we can harmonize educational standards. There's also a series of books published by members of our working party or former members, which help with the education of new reaction engineers. If we look at governance, then we have a structured governance model. So We use the typical model, which is used by most of the EFCE working parties, and this ensures we have organized leadership and decision making. So we follow the rules of the EFCE working parties. We focus on diversity for the membership composition. So we have people from the national societies, but both from academia and industry. So we try always to have a balanced membership composition with people from academia and industry. Yeah. Next to that, we have a rotating leadership role. So we have a chair and a secretary, but these rotate every so many years. And we also focus on consensus-driven decision-making. For example, for selecting the new location of the new EastCRE conference or the ESCRE conference, we try to come up with the consensus. Obviously, that takes sometimes a bit of time, but in the end, that's beneficial for the whole working party. If you look at awards, then we have an EFCE Excellent Award in Reaction Engineering. The last one was awarded in 2018, and this is something we are picking up again as the working party. And so on our next ESCRE meeting, we hope that we can award to one of the more youngest people, researchers in reaction engineering, this EFCE Excellence Award in Reaction Engineering. Yeah. Of course, we promote excellence, and we are very happy that many of our members hold ERC grants or other prestigious grants. And we also make sure that our community is well represented at international conferences like the AICHE meetings, and that also there the reaction engineering community of the US and Canada meets with the European reaction engineering community. We try to push also innovation, and we really encourage this innovation and ambition, and we also try to illustrate how we can innovate with reaction engineering our field. Yeah. So why does CRE matters? I think it really is a key element of chemical engineering. It really focuses on reactors, and if you look at important societal challenges, then think about CO2 emissions, then these are typically associated with reactors. So if we can develop new technologies, more intensified, electrified technologies, which are more sustainable, then I think we really make a big step forward in the European, but also in the global chemical industry. Yeah. And this is really a strategic platform for growth, our working party. So, and I think we can really demonstrate that we can solve real world problems. And I think Jan will elaborate on that further. So this is what I wanted to share. Thank you for your attention.
Yeah, thank you very much, Professor Van Geem. I think, Jan, you can share your screen as well.
Okay. Okay. I hope you can all see my screen. There was a small thing that I wanted to add, and I thought Kevin was going to show something like that, where we see that the reaction kinetics is a scientific area in which we combine many different techniques. We need to have very different analytical techniques to understand what is happening. We need to have also an idea for thermodynamics, also on flow hydrodynamics in the reactor, and so on. So I wanted to illustrate that with an example of a process development of production of renewable fuels from vegetable oils. So a few key steps that I was going to highlight was if we have a reactor engineering problem, a catalytic process in which we want to do some developments. So here it's transforming these vegetable oils into biodiesel or renewable diesel, or to sustainable aviation fuels. We have several things that we need to look at during the process development. First of all is, of course, the material science, where we have to develop high activity catalysts. And I'm going to illustrate each of these a little bit further on. Then, of course, we need to know what is going in and what is going out. And so we very often need to use advanced analytical techniques. We also need to understand what is happening in the reactor. So we need to do experimental work trying to identify which molecules are being transformed and what we're going to see, and then implement all of this knowledge into a kinetic and reactor model. And the reactor model will also show that we need to look at some flow dynamics inside the reactor. So as many of you will know, of course, we have an active phase in a catalyst. So in this case, in this example, it is a cobalt molybdenum catalyst or nickel molybdenum catalyst. This catalyst, this active phase, has to be inside the reactor, supported on a particle. In this case, I show the example of a trilobe. And when you zoom in into the different scales, you can see that these active phases, you will support them on a porous phase, in this case in alumina. And if you zoom further in, you will see that you have both the alumina phase and the cobalt molybdenum or nickel molybdenum sulfur slabs that will do the catalytic work. Developing catalyst is, of course, quite intensive. You need to test and screen different things. And the idea is that you want to optimize all the way down to improve the yield of the product that you want to have at a given conversion level or a given severity. Now, to look at the process development, one of the things that is important in scale-up is that if you have a small amount of a component that is not very important in your development phase, you will very often ignore it. And one of the things that you will have is that when you start to scale up, even if you have 0.1 weight% of some waste material, if you start to be working with hundreds of tons per hour, then these 1% become tons per hour. And so you have to do something with that. To do that, you need to identify the different components. One of the techniques that has helped us over the last 10, 15 years a lot is comprehensive GC by GC, where we have a separation in 3 dimensions, boiling point, polarity, and concentration. So most of you already know this. In the case of the example that I'm looking at, the production of renewable diesel and sustainable aviation fuels, the feed is, of course, much more simple. If you look at from a wide perspective, it is mainly triglycerides. But as I said, minor components in these feed can pose you some problems when doing the scale-up. So you need not only to look at the main components and do the experiments with model components, you also need to use real feeds which have some dyes, some sterols, some vitamins, some metals that can have some surprising effect on the reactor performance and on the catalyst lifetime when you are going to scale up. Understanding the chemistry means that you need to do also some work on pilot plant experimentation, which means that you need not only lab scale equipment, but also higher scale equipment. This allows you to have sufficient amount of feed and effluent to measure the cold flow properties or the different properties that are important for the industrial application. So that's why you need to have not only lab scale equipment, but also larger scale equipment that allows you to get higher volumes and to measure properties that you cannot measure simply by chromatographic analysis or other lab analysis. For the sake of time, I see that we have already spent quite some time. I'm going to skip on this specific example. We will look at the different catalytic steps. So the process in this transformation of vegetable oils into sustainable aviation fuels has two steps. The first step, in which we are going to remove the oxygen part and the glycerol part from these lipids to have some straight chain paraffins and some branched paraffins. But the thing is that when you just remove the oxygen and you get these straight chain paraffins, you have a wax which is no longer a sustainable aviation fuel. It's no longer a liquid. And so the typical example we give is that normal hexadecane has a melting point at 18 degrees Celsius at ambient temperature, while an isomerized paraffin with the same length, 3-methylpentadecane, has a melting point of minus 23 degrees Celsius. So just removing the oxygen, making the paraffins is not enough. You need to isomerize them in a second step. And so by doing that, to improve the cold flow properties, what you are going to do is to isomerize more and more the molecules so that you can reduce the freezing point, the melting point, so that you can use it really in a jet fuel application. Then, of course, once you have done enough experimental work, you need to unravel the kinetics that are happening and to determine the rate coefficients and generally implement this kinetic model into a reactor model. So I've shown you I've talked a little bit about the kinetic model, but of course that's not enough. Here we will have a three-phase system. You will have hydrogen, you will have a gas phase, a liquid phase, and so over a solid phase catalyst. So what we're going to do is we're going to develop a reactor model in which we have these hydrodynamics accounted for, looking at the gas-liquid equilibrium. And if the reactions are really too fast, we are going to look also at the transfer between the gas phase and the liquid phase. This kinetic model will then can then be used to look at scale up, to look at optimizing the reactor configuration, the operating conditions, and so on. One important point is also that we need to look at the flow inside the reactors. As I said, we have a three-phase system. And in a three-phase system, you need to, if you have a fixed bed reactor, you need to uniformly distribute both the liquid phase and the gas phase that you have entering the reactor. To do this, we need to look at distribution of gas and liquid in a downflow reactor. And to do this, we have done extensive cold flow model testing, so CFD modeling, and also get feedback from industrial units. An example of the work that we did here on flow hydrodynamics is using gamma ray tomography on a relatively large scale. So we have a reactor that you can see over here, which is about 10 meters long and about 0.6 meters in internal diameter. We can fill this up with different types of catalysts or luminous supports. And then we have a gamma tomograph that can rotate around the reactor to take an image of the flow inside in less than 2 hours with a very high resolution. And you can also move the gamma ray tomograph vertically to look at how the flow or the distribution of gas and liquid evolves from the top to the bottom. And so here are two examples. An example in which you have a relatively bad distribution. So we can see that we have injecting gas and liquid in different phases. So here you see the liquid fraction. And on the left-hand side of the picture, you see that you have really liquid jets that are flowing through. And then you have gas phase around it, which means that in such a case, some of the catalysts will not see the liquid. And so will not be able to promote the different reactions that we want to catalyze. On the right-hand side image that you have over here, you have an optimized distributor, and this optimized distributor gives you a much more uniform flow, distributing almost perfectly the gas and the liquid over the entire fraction. So that's also a very important step in scale-up, where you need to look at not only what's happening on the active site, but also what's happening with the flow inside your reactor. And so that's about the end of my industrial presentation of what we do to do catalyst development. So here in this example, we talked about producing producing sustainable aviation fuels and renewable diesel, starting from edible oils, waste, unconverted used cooking oil, animal fats, tall oils. In the first step, we are going to remove the oxygen and hydrotreat the double bonds, and therefore we will obtain mainly normal paraffins. But of course, these are not usable because they are solid at ambient conditions. And then we are going to isomerize these isoparaffins to get either, as I said, renewable diesel or sustainable aviation fuels. And with that, I would like to thank you for your attention.
Thank you very much for these very nice talks. They were indeed very interesting, and I'm particularly impressed. It was nice that you highlighted also the multidisciplinary nature of reaction engineering, material science, analytics, fluid dynamics. They're all very important, and really thank you for highlighting that. After the talks, as promised, there will be a Q&A session. We will start from some questions. Maybe Alper, you can start sharing the screen. We will start with some questions prepared from the early career section, and then we will continue with possible questions from the audience. So again, I will stress to the audience, if you have any question, please put it in the Q&A box. So before, let's say, starting with more scientific questions, let's start with an icebreaker one. According to you, to both of you, if a reactor would have a personality, which reactor type would be the calm one, the chaotic one, and the overachiever? I don't know who wants to start.
Well, I don't know. I can start. You said if a chemical reactor had a personality, I think that it's a little bit with chemical reactors that we have with people. They come in different flavors, and so there are different types of reactors that you can describe. And of course, a calm, chaotic, and an overachiever can be interpreted as very different. Maybe on the practical industrial application, the calm one would probably be the CSTR reactor, because it's very insensitive to small variations at the inlet of the reactor, while the plug flow reactor is much more sensitive. Chaotic reactors, I would probably talk about fluidized bed or at least riser reactors in fluid catalytic cracking, where you have a very chaotic behavior and also a complex behavior, because your feed is vaporizing, everything is accelerating, you have very wide ranges of catalyst distribution over the entire reactor. And on the overachiever, well, it's always been the reactors in which you do have process intensification, because you are doing several things at the same time. So two of the examples that I would like to cite is catalytic distillation, where at the same time you have a reaction, a catalyst that is in a distillation column, where you do at the same time the separation and the reaction, which allows you to displace equilibrium at each step on a continuous basis. And maybe another example for me would be the isothermal plug flow reactor, which is probably the one that you have most control of. You can really select the temperature to have the selectivity that you want. I don't know if Kevin wants to add something to that.
Yeah, I think on the calm one and the chaotic one, I would totally agree. I think for the overachiever, well, we have been working quite intensively on shockwave reactors, and these basically, they come with volumetric heating. And so with classical heating, you basically heat from outside to in. And now we have a reactor that basically heats from inside to out. And that really results in drastically improved performances, even for processes which have been around for almost a century. So that really is an overachiever, or an example of an overachiever.
Yeah, great. Thank you. I agree with both of you. They're very nice explanation indeed. Okay, now we can move with the next question. And this is maybe very much related to us as early careers. We would like to know from you, what are the main differences between reaction engineering in academic research and the reaction engineering in industrial R&D or manufacturing? And maybe also how the knowledge that we get from academia can be combined in industry and vice versa.
Yeah, so maybe I can start as that. Of course, if we look at academia, then we basically start from very fundamental understanding. So we start from ab initio calculations, trying to understand the kinetics. Then we move to the kinetic model level. We use that information to develop materials, and then we make a step to the process. So we do the scale-up part. But of course, in academia, you can only go to a certain scale. And I think my group is one of the groups which can go to relatively large scale, but that's TRL5. And if I look what's happening in industry, of course, that scale-up part is substantially more important. But also the modeling part is typically also used for financial optimization. Yeah, if I look at many of the models, and for example, the models that also Jan developed during his PhD, then they can be applied to refineries or to large-scale units, and they can also not be optimized necessarily for getting the best yield, but basically to optimize to get the most value. And that's a different optimization function that in academia you would never do that. You would always optimize a catalyst for yield, and so sometimes the objective function is maybe a bit different between academia and industry.
So if I fully agree, I mean on the industrial R&D, the main driver is scale up, going to larger and larger scales. Did we forget something? Is something happening that we didn't expect? Is when you're moving to a larger scale, is in effect becoming more important than it used to be at the lab scale or the pilot scale? And then, of course, as Kevin said, the economic optimization. So in many cases, we are much less interested in intrinsic kinetics. In many cases, we also use yield vectors to look at the economic optimization instead of going to very detailed models. So I'm not saying that we shouldn't look into more detailed models. It's also the way to trying to identify the most important factor and to look at what are the things that we didn't expect when we change scale.
Yeah, indeed. Descriptors for academia and this industry might be different, and this changes objective functions, and as Professor Van Geen mentioned. So thank you very much for your insights. I will ask the next question, and then I will give the floor to Alper. What career paths are available for people specializing in chemical reaction engineering, both from academic and industrial perspective?
Yeah, well, I'm very fortunate to have a large number of students, and both PhD students and postdoctoral researchers, and their careers are very diverse. So many of our PhD students, they in the end join chemical or oil companies. Where indeed the aspect of scale up is still very crucial. But also the aspect of modeling. Sometimes small deltas can make enormous differences in financial for companies. So we have many of our graduates go to the larger companies, the BASFs and the ExxonMobil, the Total Energies of the world. But then, we also have the entrepreneurs, and they go to either new spin-offs. One of my PhD students who will graduate next week, he will join a spin-off in Berlin. So basically, that spin-off is working on ESAFs. And I had also students really starting their own company. And I think that's basically the freedom that you have with this degree. You can also go for an academic position, but of course the academic world is well, it is competitive, and so the number of places as professor are limited, and you really need a bit of patience, and you need to be mobile. So sometimes the vacancies, there's I think a nice vacancy coming up for a professor in reaction engineering, but it's in Finland, and Jan is an exception for a Belgian. So Jan actually moved to a different country to get a different position. But for example, most Belgians, they like to stay near their church. Voilà, I summarized. So it also depends on your personality, what are the possibilities. So academia is for sure possible, but you need at least to be willing to relocate. So maybe Jan, you can add something.
Yeah, in industry, I mean, it all depends on what you want to do. As Kevin said, there are many opportunities for a chemical engineer or a chemical reaction engineer. Career paths in industry, you have, if you want to do R&D, well, let me tell you, there are a very limited number of places in general. So it's difficult to have an R&D career in industry because it's not their main objective to develop new technologies or to look at developing entirely new pathways. Many people that go to industry go to production sites, and so the main skills that you will need to use, of course, besides your chemical reaction engineering background, which is always important to analyze the problems that are happening on the units, is managing groups of people and trying to improve the process at the same time. But the managing skills become more important if you go into industry and you have less time or less opportunities for R&D, especially today where short-term revenues are more important than long-term.
Okay, thank you for very much for your honest opinions. I think they are very useful for me also, and I think for all the audience. So, okay, I will give now the voice to Alper. He can continue with the Q&A.
So we have just one question left. Let me ask this. Where AI can bring substantial improvements in chemical reaction engineering, what are the threats for both of you?
Yeah, if I look at AI, then well, you obviously think about speed up, and but okay, there's also I think the risk of going to black box models. Voilà. And the field of reaction engineering is in the end where we really try to avoid black box models. Yeah, and so yeah, reaction engineering is all about getting good data, and then we can develop very detailed models. And for me, AI can help to, for example, in CFD simulations, to speed up these simulations substantially. But in the end, then, yeah, because the models that we develop are really typically quite advanced, then the big benefit of AI on precision, I think, is limited in our field. Yeah, but it can help us to maybe come up with new technologies. It really is. Yeah, if you look at if you have to create programs or software, then if you do that now with AI, everything goes so much faster. We really see a huge impact in the field of the pharmaceutical industry. Yeah. So in the pharmaceutical industry, processes are substantially less optimized. You have multiple pathways to make the same API. And there really the AI can really help you to select more optimal pathways or new conditions, and also reduce waste substantially. So I think in the classical petrochemical industry, I see less impact. But then other fields, like in the pharmaceutical industry, I see big impacts of AI.
So if I had to add something to that, is AI, you shouldn't forget that it is a tool. It is not something that that you have to. You shouldn't allow AI to replace your chemical reaction engineering fundamentals. The fundamentals need to be there. It's like doing a calculation, and you need to have some reflexes to know that something is happening. If I calculate some reactor and I find a number that is out of my normal field, I will start I will have something, a bell that is ringing, saying, okay, something's wrong here, something's wrong in the calculation. Well, with AI, it has to be the same. It will be a tool that will be able to accelerate, but it is a tool, just as calculators, computers, internet. So has been a tool that allows us to accelerate. AI will be a tool that allows us to accelerate, but you shouldn't forget the fundamentals. And as a user, you will always need to critically assess what are the numbers or the data that are given. So the threat that I'm feeling is that I'm a bit worried that if people start to use these tools as black boxes without thinking, that we will have some some fundamentals that are lost, and we will not see if something is going wrong. So you need to have good fundamentals to be able that if you see something that is a bit weird, that it rings a bell and that you're going to check the data, the calculations, the outcome, and to understand why this was given and why it is wrong, or at least strange. So that's a little bit the good side of AI will be acceleration in many domains. The bad side in AI will be, we need to be careful that we check that the outcome is a reasonable outcome. And I would like to add something to what Kevin said on the pharmaceutical industry. AI is indeed becoming very important in the pharmaceutical industry. And I think this is because chemical reaction engineering has been absent in the pharmaceutical industry. Pharmaceutical industry has been dominated by chemists, and now they discover things that they call flow chemistry, which is in fact plug flow reactors. And so because it was a domain where chemical reaction engineering has been absent a lot, now with AI, they discover chemical reaction engineering principles through the use of these tools because we weren't there. That's one of the things that is a bit worrying also, that people rediscover things that already exist in other fields.
I think I really like your statement, Jan. I think that's
Thank you.
So thank you for your responses, and we come to Q&A session, and we have one question from Ahmed, and the question is a bit related to our last question under AI condition. Dr. Verstrode, I was looking at the work iPhone is doing with Carmen Joint Lab. I'm really curious, how do you approach the challenges for energy transition, there particularly with softwares? Are you using Aspen, Aveva, or bridging the analytical modeling, integrating the AI?
As it is a growing field, we are using many different tools. Yes, we are using Aspen. Yes, we are using different tools that exist, also open source tools. So it's something that we are continuously trying to use to benchmark, also for analysis of literature, summarizing things. And so, yes, also in the modeling part, we are working on physics-informed neural networks, on machine learning with large data sets. So we have different people trying to evaluate where we can accelerate using these tools, these AI in general. So, and of course, today, mainly the main part of our work is on the energy transition. IFPN is working both on renewable fuels, is working on recycling of metals, recycling of plastics, and so on. So these are domains that we are trying to use AI to accelerate our developments.
Yeah, thank you. For the sake of our time limit, unfortunately, we couldn't take more questions. So you could send your questions to us, and we will reply these questions soon. So thank you again for your time, and especially I want to thank Jan and Kevin for making this presentation, making this meeting very informative and fruitful. Thank you.
Thank you very much.
everyone.
Thank you.